Okay, let's unpack this. You probably think you know ice. It's cold, it melts, it insulates. Pretty straightforward stuff, right?
Adds to the common view, absolutely.
But what if this everyday substance, this frozen water, held a kind of secret electrical life? Today we're diving into some really groundbreaking research. It's revealing how ice can actually generate electricity in some truly surprising ways.
It's fascinating because while common ice, what we call ice, isn't piezoelectric, a uniform squeeze doesn't electrify it.
Right, the charges cancel out or something.
Exactly, because the hydrogen bonds are disordered. But new discoveries confirm it does possess flexoelectric and even surface ferroelectric properties.
Flexoelectric.
And ferroelectric. It means ice can become electrically active under very specific kinds of stress or temperature conditions. It changes the game.
And that's really our mission today for this deep dive. Explore these hidden electrical capabilities, understand the mechanisms, and see why they actually matter for, everything from new tech to maybe even lightning storms.
Precisely. The implications are quite broad.
So let's start with that first one. Flexoelectricity. We usually think ice is electrically, dead to pressure. But that's only part of the picture.
That's right. It's not about uniform pressure. If you bend ice, you create what scientists call a strain gradient.
A strain gradient, like stretched on one side, squashed on the other.
Exactly. And that generates electrical polarization.
Okay, so how much electricity are we talking? Is it tiny?
Well, it's surprisingly robust, actually. The measured flexoelectric coefficient is about 1.14 plus or minus 0.13 nanocoulombs per meter.
Nanocoulombs per meter. Doesn't sound like much, but what does that mean in context?
It means ice is quite sensitive electrically to this bending. Its response is comparable to, advanced ceramic materials, things like strontium titanate, titanium dioxide.
Wow, materials designed for electrical uses.
Yes, exactly. Materials specifically engineered for those properties. So ice is sort of a natural transducer.
A natural transducer.
And we also see this effect isn't constant. It changes with temperature. There's a peak around a really cold minus 113 degrees Celsius.
Minus 113 C. Okay.
And interestingly, it also increases again as it gets closer to melting, probably because of a thin sort of quasi-liquid layer that forms on the surface.
Right, that pre-melting layer. Okay, so ice generates electricity when bent. But the next finding, this sounds even more unexpected. You mentioned ferroelectricity at the surface.
Yes, surface ferroelectricity. Now, ferroelectricity is a property where a material has a spontaneous electric polarization, basically, a built-in electric field.
Like a tiny magnet, but electric.
Sort of. And the key thing is you can reverse that polarization with an external electric field, like a switch.
Okay.
The really groundbreaking part here is that this was observed quite unexpectedly, around that same temperature, minus 113 C or so. But it's not the whole chunk of ice.
There's the surface.
It's just a super thin skin layer right near the surface. Almost like it has a different electrical personality just on its skin.
And I think I read the material touching the ice matters too. The electrodes.
Absolutely crucial. Yes. The choice of electrode material significantly changes things. It depends on something called the work function of the metal.
Work function?
Yeah.
How easily it gives up electrons?
Basically, yes. Platinum electrodes, which have a high work function, hold electrons tightly. They showed a much bigger effect, about 15 nanocoulombs per meter near minus 115 C.
15. That's way higher than the baseline flexoelectricity.
It is. Gold, with a lower work function, gave about half that. And aluminum, lower still, showed no peak at all.
Interesting. So it suggests electrons moving between the metal and the ice are key.
It strongly points to that, yes. Interfacial electron transfer seems to be critical for activating this ferroelectric behavior.
And how do we know for sure it is ferroelectricity? What's the proof?
The smoking gun. It was a very distinctive electrical signature they observed. It's called a butterfly hysteresis loop.
Butterfly loop.
Yes, if you graph the response, the curve traces out this unique shape like butterfly wings. That's the classic hallmark, the undeniable sign of ferroelectricity.
Got it. Like a fingerprint.
Exactly. And powerful computer simulations, ab initio calculations, they actually back this up. They showed that these metal interfaces stabilize a polar form of ice near the surface.
And they matched the experiment.
They did. They even predicted the thickness of this skin layer, maybe 15 nanometers for gold, 35 for platinum, which lined up really well with the experimental estimates.
This is all fascinating science, but the listener's probably thinking, okay, cool, but so what? How does this change how we understand Well, lightning, for instance.
Right, the real-world connection. While calculations strongly suggest that flexoelectricity, the bending effect, likely plays a pretty big role in charging up thunderstorms.
How?
When ice crystals and grapple, those sort of soft, icy pellets collide up there, the impact creates that strain gradient, that bending.
Ah, okay. Collision equals bending equals charge.
Huh. That's the idea. And the amount of charge calculated from this flexoelectric mechanism, it's around 10 to the minus 4 coulombs per square meter. That number is remarkably close to the actual charge transfer measured in experiments simulating those collisions.
Wow. So it could be a primary mechanism.
It seems very plausible, and what's more, it also fits with something called temperature-driven polarity reversal.
Where the charge switches.
Exactly. Why grapple particles sometimes charge negatively and sometimes positively depending on the temperature and conditions. Flexoelectricity offers a potential explanation for that switch, too.
That's incredible. A possible key to lightning initiation. Beyond storms, though, what about technology? You mentioned transducers.
Yes, these electromechanical properties could lead to new kinds of sensors or energy harvesters. Think about low-cost devices that work in really cold remote places, maybe space exploration, polar science.
Where conventional sensors might fail.
Potentially, yes,
Yeah.
using ice itself or materials mimicking this property.
So pulling this all together,
Yeah.
what's the big takeaway?
Well, I think the biggest picture is that ice, this incredibly common material we thought we knew, is far from inert. It's electromechanically active in complex ways we're just starting to appreciate.
It fundamentally changes how we should think about ice.
It really does.
So wrapping up, the fact that ordinary ice has this hidden electrical dynamism, it really makes you wonder, doesn't it? What other plain materials out there have extraordinary secrets waiting? Properties that could, reshape our science and maybe spark totally new innovations.
A very good question. There's likely much more to discover.
Keep exploring, and we'll keep diving deep.